Thank you for coming back. Quick reminder that if you have a question, raise your hand and the microphone will pop up on your hand. So everyone, even people that are online, can hear us. Okay, good. Thank you for coming back. Today we finish what I had planned for my first lecture. There's not much left. And then we start second lecture, and the same is valid today. I don't mind if we don't come to the end. We still have tomorrow. Yesterday, I started by telling that I have not much to do with quantum computation. And Celso told that you have a focus on quantum sensors. This morning on Archive, the repository for preprints, there appeared a paper from a Russian group that are using cold atoms to sense magnetic fields, really to map stray magnetic fields in a given environment. So it's a coincidence, but it's a happy coincidence. Okay, yesterday we finished the treatment of an interacting BEC in a trap, and we finished by writing the Gross-Pitaevsky equation. So let me just remind everyone where we were. So we were writing the Gross-Pitaevsky equation that governs the motion of this many-body wave function, so that we called zero, and it's like a one-body wave function that have under it a very large number of single-body wave functions. Okay, so that's how we write it. So I write the time dependent first, and then the time independent version. So we all know where we were yesterday. So an external potential, psi 0, plus this, which is effective potential that is due to the interactions. So it's a mean field coming from the interatomic interactions. It only depends on this parameter, which is the S-wave scattering length, and it's essentially the billiard ball potential. So, and the density of our gas. Okay, this is time independent, and then we wrote time. This is time dependent. We wrote the time independent, and we have chemical potential here. So, and we wrote it like this. So I'm short here, but you know that this C0 depends on RNT, and this is only on coordinate space. Okay, good. So external potential times this, and then again, and I'll be shorter. We usually write G as a coupling constant here, but we are writing this guy, okay? Okay, good. I told you that this Gross-Pitaevsky equation models almost everything in quantum gases. Almost, really almost everything. The agreement of theory and experiments, theory based on this, is just great. It's funny because we can have, it's a nonlinear equation. No, there is a nonlinear term here, and it's solvable, but not easy to solve. You can solve it computationally and so on. But the main solution for the ground state is analytic solution. Because as you might expect, we're talking about very low energy systems. And very low energy, very low temperature means that kinetic energy is very low. So I can make an approximation called the Thomas Fermi approximation, where I throw this away. Okay, we can be a bit more formal, and we can estimate the ratio between kinetic energy and interaction energy. So between this and this scales, this is proportional to a quantity that is oscillator length, I just define what it is, over the number of atoms times the scattering length to the 4/5, okay? So, and this oscillator length is just, it's easy to know what it is, but if I solve this equation without interactions, this is in a potential that is a harmonic oscillator. The wave functions are Gaussian, so the oscillator length is the width of this Gaussian. So it's the size, the typical size of the system when there are no interactions. So this is h bar over m omega to the half, okay? But what's important here is that if I increase the number of atoms or if I increase the interaction, very quickly interaction dominates over kinetic energy. For practical purposes, if I have 1,000 atoms and a typical, I don't know, rubidium atom or sodium atom, which were the first ones to reach Bose-Einstein condensation, I'm already in this regime where kinetic energy is negligible, okay? So when I do it, I get rid of this, and if we remember that this is density, I can rewrite this expression. So getting rid of kinetic energy is called the Thomas Fermi approximation. Thomas Fermi approximation. And when I have this, I can go with everything to the other side, and what I get is an equation that looks like this. Psi 0, V trap, plus G. G is the coupling constant for the interaction, times density, what it is, minus chemical potential equals 0, okay? This has two solutions. Either psi 0 is 0, or this is 0. There's no way around. And if I have this as a 0, I can just solve for the density, and I get the density equals to mu minus V trap over G. Why this is important? Because now I have a density distribution that is the inverse of my trap. So if my trap is a harmonic oscillator, my density distribution is an inverted parabola. Do you see this? So I think it's easy to see. But this is interesting because this was the smoking gun that everyone was looking for when looking for these things in experimental systems. So if the density distribution of my system changes, I may have a Bose-Einstein condensation. So this is what was seen before. So I'm showing you first one picture of classical gas. So this is above the critical temperature. So this is a picture of this is a shadow. Can you see the shadow well? Yes. This is a shadow of a classical gas. So a gas of bosons above the critical temperature. I just have released this from the trap and let it expand for some time. And then I take the picture. So this is what you're seeing. When I do it, if this gas is classical, kinetic energy dominates, and the density distribution is a Gaussian, and it's round. Okay, it's the same in every direction, and it's a Gaussian. So this comes from Boltzmann statistics. Okay, I'm just looking to velocity distribution there. I can make a cut and look for this density, and this is a Gaussian. Okay, this is experimental data. And then I can do it when I'm below the critical temperature. So this is, again, it's just false color, so the white means nothing. It's just a different color code. But white there is, again, density. And again, I'm taking a cut. And when I do it, what I saw is, you see, you have a Gaussian that is fitted in blue. You have only the wings of this Gaussian. This is the thermal part. These are the atoms out of the condensate. And on the middle of it, you get a parabola. And this was really the smoking gun that proved that, okay, here I have a Bose-Einstein condensate. This is a signature of it. If I cool this more, I'm here on this side. So if I cool this more, I get a smaller thermal fraction. If I cool this a lot, I barely see the thermal fraction, and I have a perfect parabola. Because this is on the bottom of an harmonic potential, so a parabola. So our density distribution is an inverted parabola. Okay, good. This is the Thomas Fermi solution. But if you are a bit more, if you like mathematics a bit more, no, you notice a problem. Instead of using this, I'm drawing here this. So I have density times, I don't know, versus x, get one direction, okay? And this is a parabola because I'm thinking that this trap is harmonic potential. So this is an inverted parabola. This is an inverted parabola. But density cannot be negative, so what happens when it reaches zero density? It has to be zero everywhere else. Okay, this is what we are seeing there. And this is a problem. Who can tell me which problem there is in there? I have a discontinuity here. Cannot. No, you know that discontinuities are very nice, but we cannot allow for it. No. And actually, this is the last thing I want to define to you. Of course, when density is low, this kind of approximation is not valid anymore. So I cannot disregard kinetic energy at the edges of my condensate. So it was defined a typical length scale that is called the healing length. So it's where the wave function heals. No? So the healing length. And it's interesting, healing length. Okay? It's interesting because the healing length, we are defining it to solve this problem, but it's the typical length where density is varying. So if I have, like, if I drill a hole in my density, okay, for any reason that we come back soon, this hole has a size, and the size is the healing length. So it's a length associated to variations in this in the density distribution, and I can estimate the healing length by estimating how much is the kinetic energy compared to the interaction energy on this region. They should be comparable. As soon as I go up in density, then of course kinetic energy doesn't play a role anymore. Okay, so kinetic energy in a length here that I call Xi, I think. I never know these letters. Okay, is on this order. And the interaction energy is of this order. So the healing length, whatever this is, this letter is this size. 2mg over n. I think it's all right. So typical density fluctuations on a BC have this size. This is the message. Okay, very good. I think this brings me to the summary of this part. So you have seen the Gross-Pitaevsky equation. Again, G is defined like that. We have plugged in the typical time-dependent solution for this, and we get the time-independent, and the Thomas Fermi solution. This is the take-home message of this part of interacting BECs in a trap. And this, of course, brings me to the end of the first lecture. That should be yesterday. So today we go for the second lecture, and our plan for today is playing with Bose-Einstein condensates. Okay, yeah, this is the plan for today. So just a reminder of what we did yesterday. I told you that a Bose-Einstein condensate, actually ChatGPT told us, no? It was my second slide. That it's a purely statistical phase transition. It's the macroscopic occupation of the ground state. This I think I've showed you. I think I have convinced you of this. Is the dominance of the lowest energy mode of a boson field. It's a spontaneous break of symmetry. I think you all see this because I'm really piling up particles in a single mode, so I'm breaking the symmetry of my system. But ChatGPT did that this was a giant matter wave. Did you believe it? I mean, is this a giant matter wave? Is this a superfluid? Because this was in the definition that we read yesterday. And somehow I looked at this and say, okay, I did not convince them that this was a superfluid or this was a giant matter wave. So I think I should do it before we start playing with BCs. So is this really a wave? If you have to prove that something is a wave, what you would do? Sorry again? You show that it's obeying a wave equation. Yeah, but okay, experimentally? Interference, yes. This is what I would do. No, I'll try to interfere those things. And this is what experimentalists did. So interference. So we got a potential, and this is a cartoon. So you see, this is atoms in a potential. We cool them down, this is a BC. See, this is how experimentalists see a BC. And then you split the potential, this potential. In a sense, we are already playing with this equation because I'm splitting this potential. I'm making a double well. And I let it go. When I turn the potential off, this will expand because there is no potential. This will expand because there is no potential. So if these are waves, there should be an interference pattern. So this is old. But I always get amazed when I see this, because at every point I'm summing matter plus matter, and there is nothing on some places and matter on the other places. So this is a matter wave. Of course, the causing of interference is diffraction, and I could do diffraction. On top is an experiment. On the bottom is a simulation. So this is you shine a diffraction grating made of light on this, and you see diffraction. So this is a wave. This is a giant matter wave. Okay, so I think if you're not convinced by this, I don't know what will convince you. Okay, and also, okay, this is something else. So you see that what is predicted by theory, simulation of this equation here, is quite good. Fine. Okay. There is another way. There is another wave property that we studied in our undergraduate course. There's, if I have a wave packet that is very narrow in space, it has many momentum components, so it spreads quickly. No? So if my wave, if my density, my C0 is anisotropic, like squeezed in one direction and less squeezed in the other, if this is a wave, the more squeezed the direction will expand faster. Do you see this? Okay, so let's switch off this and let it expand. If I do it with a classical switching off, if I do it with a classical gas, this is again a gas in above TC, above critical temperature. It is anisotropic because my trap is by chance anisotropic, and when it expands after a very long time, it's round. It's not a wave, it's a gas. If I have, these balloons, they can be anisotropic. If I explode, then this gas will expand and eventually be isotropic. But if I expand quantum gas, it's anisotropic, and at some point, this direction was smaller, and after some time, this vertical direction is larger. Do you see this? One can actually compute this, just divide one direction by the other, and this is what we call aspect ratio inversion. So the classical gas goes to 1, the quantum gas goes from below 1, so dividing this direction by this direction to above 1. This is a wave. This is a wave. Sorry? No? Because I have a wave a wave packet that is very compressed in one direction. So it should expand quicker in this direction. It's a Fourier transform, no? Okay? Everyone? Good. Okay. So we have a wave. But still, we don't have a superfluid. When I think about, well, we don't. We do have, I just haven't showed you. When I think about a superfluid, I think about helium. No, everyone has seen helium, liquid helium superfluid in YouTube and these beautiful experiments. No liquid helium going up walls and so on. So can we show that this is a superfluid? Indeed, we can show. We go back to the blackboard to show that this is a superfluid. So what I'm going to do is first to show that this Gross-Pitaevsky equation has, we'll show that we can manipulate it to show that this has the structure of a fluid equation. So it will be a fluid, okay? I should have not erased it. So E I H bar deep psi dt. So we show that it's a fluid. So this plus potential times psi g density psi, okay? I'm dropping the zero just to be quicker. So I'll multiply everything by the conjugate. So I will have I h bar this equals to minus h bar 2m. The conjugate Laplacian plus v conjugate this plus g psi square conjugate times this, okay? Then I write the conjugate equation. So I write the Gross-Pitaevsky for the conjugate and multiply by psi, okay? I do have to write it. I think, so did everyone see this? So I write the conjugate equation and I subtract one from the other. Okay, this is the step. And when I do it, I get an equation that looks like this. I h bar like this on one side, and on the other side, because I subtract this term is canceling, this term is canceling, and I have this psi Laplacian psi minus this thing, okay? I can reorganize this and I get, okay, I have h bar here, h bar squared there, I have an I here, it will come down here, okay? This is the derivative of the product, time derivative of the product, and this I can play with it to have divergent here, okay? So what I will get is this, d dt psi equals to, so I write different, I write plus, because there is a minus, so I come to this side with a plus, h bar over 2mi. This will pay off, okay, again, I hope. Plus divergent of this. This gradient psi minus psi gradient And then I close, and then I close. Okay, good. So time derivative of density plus the divergent of something. This equation has the structure of equation that you probably have seen many times in your undergraduate course. You have seen it written for charges. You have seen it written for mass. This equation is the same of this, which is the continuity equation. As far as my velocity field is defined as h bar over 2 mi psi square, and then that term here. C gradient C minus. So first equation that I wanted to show to you is that our quantum gas obeys a continuity equation just like a fluid. Just like a fluid. Okay, fine. Okay, second one. We know that C is a complex function in general. I can write a complex function as a norm times the exponential of the phase. Oh, this is how we write complex numbers. So I can write G, I can write psi as square root of n exponential of I times phi. So you see that if I write psi by psi star, I get the density. Okay, this is easy. And I'm not doing it explicitly, but it's not a difficult calculation. You could do it this afternoon. We can do it together if you like. But if you plug this in here, we get the velocity field. The velocity field is h bar over m, gradient of the phase. Keep this. We use it. But we can also plug it in the in here, directly in here. I can use this solution because it's not specific for fluids. I can plug in the solution in here. And when I do it, I get an equation that is very similar to Euler's equation for hydrodynamics. I write it now. So we get dv dt. So I'm plugging this here. Okay. I have equals to minus 1 over mn. This is mass, this is density, this is pressure. I will define pressure, okay, on these systems. V2 over 2 plus 1 over mass. I write in the next line because it's a longer expression. 1 over mass, gradient of h bar over 2m square root of the density, Laplacian of the density, minus 1 over m gradient of v. Okay. where we have defined pressure, just like we define pressure in thermodynamics. It's the derivative of m's minus, what is it? The derivative of the energy with the volume. And this is, what is it? Here. N2 G, this is G over 2, okay? This has the same structure of the Pascal hydrodynamic equation with two differences. Do I have to write Pascal equation? I think not. Okay? This term is there. This term is there. This term is there. This term is there. Okay? This is extra, and this is a term that we call quantum pressure. This is due to variations in the density. This is quantum pressure. Second, on Pascal equation, we have the rotational of the velocity, a term that is rotational of the velocity. We'll come back to this in a second. Okay? So I hope at this point that I have convinced you that this is a fluid. Because from the Gross-Pitaevsky equation, I get continuity equation and a hydrodynamic equation. Okay? But is this a superfluid? If I have to define a superfluid to a kid, I would say, okay, it's a fluid that flows without friction. But I don't have walls, so I cannot make this flow and measure friction. Is there something else? A superfluid is something that you cannot rotate. So if you rotate liquid helium, it's the container rotates and the liquid stays steady. So it's irrotational. It's a property of a superfluid. But I know how to rotate this thing. Let me see. Yes, so we obey fluid equations. This is what we did. Superfluids are irrotational. I know the velocity field, so I can calculate the rotational of the velocity field. It's in there. It's identically zero, because the rotational of a gradient is mathematically zero. So this thing is irrotational. So it's a superfluid. Yes, question.
Thank you, Professor. My question is, because you have a gradient field, you can define potential, such as a thermodynamic potential, as you can derive the macroscopic properties of the Bose-Einstein condensate?
Again, I have a gradient of the phase of my wave function. So this wave function has a norm and a phase as any. So the velocity field is just the gradient of the phase. So, and this is, so in principle I can. There's nothing against it. Okay, it's just the phase of the function. Mm-hmm. So this is irrotational. Can I test it? You have a question? No. Okay. You have pain in your shoulder. Okay. Can I test it? Can I rotate this? What happens if we rotate? It doesn't move, it's not rotating. But if we rotate very fast, what happens to liquid helium if we rotate it very fast? It develops vortices, okay? So before showing you how we rotate a Bose-Einstein condensate, well, we have an external potential here, no? So if we have a potential that looks like, you know, a spoon, I can rotate this thing, and we do it. And when we do it, we see quantized vortices. These dips in the density that you see are vortices. You know the size of these? I have erased. It's the Rayleigh length. If I rotate faster, I have more vortices. Ah, it's here. Thank you. It's here. This is the size. If I rotate faster and faster, I have more and more vortices. At some point, I have many of them. And I don't understand much the physics of this, but I know that this is the same physics of quantum Hall effect. So I can study quantum Hall effect in this kind of system. And these lattices have a regular pattern and so on. Just like helium. This is a superfluid. Each vortex carry one quantum of angular momentum. Actually, the appearance of vortices is such a smoking gun for superfluidity that there is a famous experiment. So let me try to explain to you. So if we have fermions are not superfluids. But if I bind two, this is a boson, and this can be a BC. But how can I prove this is a BC? This is a superfluid. I rotate. People use this as a proof that they have a BC and a superfluid in a fermionic system when you bind two fermions. It crystallizes. It has really a crystallization pattern in there. So it's a superfluid. Okay, now I have everything checked. Good. So this is misleading. I'm pretending that I'm starting the second lecture here, so because we are playing with the Gross-Pitaevsky equation, but that's not true. We are already playing with it. When we switch off the potential and let it expand, we're playing with it. When we rotate, adding an external potential, we are playing with it. So we are already doing our second lecture. Okay, let's see what we have for today. Just before, someone yesterday asked about solitons, solitonic solutions. Soliton is a solution in fluids, a solution that doesn't expand, has no dispersion. Since this is a fluid, it has soliton solutions. Okay, good. So let's see. Quantum gases have been studied experimentally since '95. So it's turning 30 years next year for the first BC. And they became this rich playground for studying many things. Fundamentals of quantum mechanics. Like I've showed you, this is matter wave interference. For me, it's fundamentals of quantum mechanics. Light matter interaction, because we have to understand light matter interaction to manipulate these things. And I think the closest we can get to quantum computers is quantum simulation of other systems. So we can get this equation, plug the right potentials, and get systems that look like quantum Hall effect or liquid helium or whatever. Okay? And this has been awarded Nobel Prize in 5 occasions since then. Cold gases in general, not only quantum gases, okay? And in all those years. Good, so quantum gases have been used to study many phenomena. I have a few examples here. I have like vortices that I have shown you, matter wave properties, superfluidity, what more? Interaction control, so all these things, but not only that, but many other things. These are small examples of what we can do with these Bose-Einstein condensate systems. And of course, every group out there is focusing on one or many of these topics. I want to highlight a few that we do there in São Carlos with no much detail at this point. So systems out of equilibrium, because I can know, this is an equilibrium equation, but I can add a time-dependent potential that brings this out of equilibrium. Then you can see thermalization and phenomena like this. So also turbulence. Turbulence is funny because it's a fluid phenomena. No, I think no one will dispute that. Turbulence is a very difficult problem in classical fluids. It's a very difficult problem. You have very expensive wind tunnels to put racing cars inside, to understand how is turbulence working on these. And it's funny because it's much easier to understand turbulence in a quantum fluid. So turbulence has been studied in helium for quite some time and is studied in Bose-Einstein condensates for the last 10 years or 12 years. Also, thermodynamics. You can go back. Remember, we have chemical potential here. We have defined some pressure. You can define internal energy. So you can study thermodynamics on these systems. Really, things like specific heat, compressibility. How are these things for a quantum fluid? So one can do it. And all these three are done in São Carlos by Professor Vanderlei Banhato on these topics. We can also study low-dimensional systems. Remember, I've showed today to you an anisotropic trap. So the atoms trapped in a cigar-shaped trap. It's very elongated, and you can work on these low-dimensional systems. And we have a professor there that is working on 2D gases. Guess what? There is no Bose-Einstein condensation 2D. So you have superfluidity without Bose-Einstein condensation. So it's an interesting system, especially if you can tune your trap from 3D to 2D and see these changes. You can also look for other kinds of interactions. This is what I am doing, but there are many others, okay? So in São Carlos, we have, in quantum gases, these research lines, main research lines, but we have other professors working with cold atoms. So not in the quantum regime, but in the very cold regime, like Philippe Courtet is doing a beautiful job in light matter interaction, and so on. So, okay. So if you have a chance, just look. We've been doing some interesting things. So there are many things one can do there. But why? I think the main question here is, why can we do this much of experiment, all these experiments in quantum gases? Why there is this versatility? And the reason is already in the blackboard, because they are extremely simple. Again, undergraduate students understands the meaning of the equation that is governing the systems, okay? But they are also tunable. I can easily adjust, kinetic energy is negligible, but I can easily adjust the external potential, and I can easily adjust the interactions. So with really a knob in the lab, I can work this out. So this means I can play in many, many different scenarios. So look for very, very different phenomena on these systems. Okay, so let's see how this is going. So this is, you have kinetic energy. We defined this, but as we know, this is in 3D systems. This doesn't play a role, so we are very cold. That's not true in 2D systems and 1D systems, okay? But quantum fluctuations are important. So I'm thinking of 3D systems here. So the external potential, I told you, we can do a spoon of light. We can really do a spoon of light. A laser beam rotating in space is a spoon of light, okay? And this is not easy, this is not difficult to do, actually, experimentally. Yes, question? Yes.
Just asking about what you just said about like the interaction of lasers with Bose-Einstein condensates. I was thinking about like if you would be able to transfer angular momentum from condensates to lasers, like because you talk about the vortices that have quantized angular momentum and.
So in principle, there is no problem on that. Okay, there was an experiment running in NIST that they wanted to cool light with a Bose-Einstein condensate. So it's the same spirit. No, I think it didn't work yet, but in principle you could. So, but I don't know if it was done already. Okay, so we can tune those guys. This is one nice thing. I've been telling you, okay, let's be on the harmonic oscillator, but remember, we are very low energy. So we are always in the bottom of the potential. If I'm in the bottom of a potential, I'm always in the harmonic limit. Unless I have a box or a linear potential, the bottom of my potential, whatever shape it has, it looks like a harmonic oscillator. So I can treat my systems as in first order as harmonic oscillators. I can change geometry. I'm telling about you this in a second. And I have single or multiple trapping wells. Good. And then we talk about interactions a bit later. So let's tune the confinement, the external potential. I don't like this sentence, from prolate to oblate, because, or from oblate to prolate, because I never know what's oblate and what's prolate. But this looks like a pancake, you know? So it's compressed in one direction and not compressed in two of them. So it looks like a pancake. So it's like making one of the trapping frequencies very large and the other two comparable to each other. So I have a pancake. If the three of them are comparable, I have the three-dimensional system, just a three-dimensional harmonic well. And if I compress two of them, I can have a cigar-shaped thing. Trap that looks like this. No, it's very compressed in one direction, in the other direction, and it's not compressed in the third direction. So I have a cigar shape. So this means if I can compress this a lot, I can go from 1D to 2D to 3D physics. And depending on what you are doing, you can see it live. No, you can see the dimensionality of the system taking its role while you do it. So, because we are talking about lasers. No, laser beams more focused or less focused. Okay, it's light manipulation. Okay, so as I told you, this supports soliton solutions, and this is interesting. Solitons are waves that propagate without dispersion, but in Bose-Einstein condensates, they only exist in 1D. They are only stable in 1D. So if you go to 2D or 3D, they just vanish. Mathematically, the solution is not stable. You can, of course, study superfluids and BEC, because as I told you, when you go to 2D, the critical temperature that we wrote here yesterday, it goes to 0. So you can have a superfluid without a BEC. And this is the same in 1D. What changes? The density of states. No? And the critical temperature goes to 0. So you can look for these differences. Of course, excitations are different. When I mean excitations, I mean how this thing, let's shake it. Let's let it, so let's give it a kick and let it shake. The shaking frequencies, they change with dimensionality. You can freeze one direction, or you can freeze two directions. And this is all changing with the trap. And of course, this is what I told you before. You can study other phenomena like quantum Hall effect or things like this. Okay, good. But I can have a single well with salts. No, with in a different way. If I get my three-dimensional harmonic oscillator and do something like this, I shift the zero of the potential. What's this? This is a donut. This is a donut. And I can make a donut potential. And you see, this donut is a bit fat, but if I make it thin, this is a 1D system with periodic contour no conditions, no boundary conditions. And this was done. So this is the potential landscape. So this is an harmonic oscillator, and then you just plug in from below a repulsive potential. In the end, you know, I know that you are looking there and you see, okay, this is a wireframe plot from Mathematica, fine, with false color. But this is simulation of optical potentials, magnetic potentials, real electromagnetic fields interacting with atoms. Okay, so, and then when you plug in atoms in here, you see the donut filled up. This is an old experiment, and I didn't get the reference, but in more modern experiments, you can do this with, and you are able to tune the radius. So this white bar here, it's always the same size, it's 50 microns. So these, and these are real pictures of density, real false color, but this is density in a ring trap. You can do many things in a ring trap. One of the experiments that I like the most is you get this ring, and this is a superfluid ring, no? It's superfluid everywhere. And then I add another potential here, because we are really talking, all the time we are talking about manipulating this guy. no? Adding some extra laser that is mapped here and becomes an extra potential term, okay? So I can add another one, and I can add like a cut to this ring. Just like I added here a repulsive potential, I can add a repulsive potential cutting this ring here. So what do I have when I do that? I have superfluid on one side, superfluid on the other side, and nothing in the middle. This is a Josephson junction that is studied in superconductors. So I can study Josephson physics on this thing. I personally, I cannot. In my lab, we don't do this kind of thing. But it's done in labs around the world. So you just make this junction rotate, and you measure how is the response of this junction with the speed of this barrier. You know what you're seeing? You're seeing tunneling. Tunneling that we calculate in quantum physics A in our undergraduate courses. You're seeing tunneling. Okay, but we can go further. We can do this. And if that was a donut, what is this? This is a bubble. Or a shell, okay. A shell and a bubble are, you're changing only the thickness of your wall, no? And this is done. And I've been interested on this problem in recent years, so I'm taking some time on this. This was calculated at some point. So what you're seeing here is the calculation of the Gross-Pitaevsky equation. When I open the hole in the middle of the trap. So here the hole is 0. I have filled the Bose-Einstein condensate. It fills the space. But as I open the hole, the density starts to open. I create a boundary inside. At some point, I will have a bubble. No, atoms are only on the surface of this ball. This is calculation, and this is a cut. So you see the typical Thomas Fermi solution. You see the inverted parabola here. And as I open the hole, I get density only on the surface. So this is calculation. This is interesting because as you open, so this delta tilde here is a renormalized parameter that is measuring how much the hole is opened, okay? So at 0.5, there is a 0 in the density in the middle. So this is just how they calculated the things. And you know what's going on? We are plotting the frequency of the excitations, the frequency on how this quantum fluid oscillates as a function of this opening of the density. When the density has a 0 in the middle, so it creates another boundary, the frequencies of oscillation have a discontinuity. This is a signature of a topological transition. If you have read about topological transitions in condensed matter, these are very difficult problems that you are usually driving through interactions or through very involved parameters. Here, we're driving a topological transitions by changing the geometry of the system. Only the geometry of the system. Okay, good. But this has a problem, gravity. I mean, maybe this deserves a historical note. This kind of potential, it was planned very soon after BCs were available. So technically, it's not very difficult to generate a shell, okay? One can mix magnetic fields with radio frequency, and then if you mix them right, you have a shell, okay? Experimentally is not a big deal. So you have this potential that looks like a shell that is written over there. But this experiment stayed, I can do it only on the paper, because on Earth you have gravity. So if you put this fluid on a shell, it's like a bubble. If you ever played with a bubble, what happens to a bubble? It starts to drop from below because the liquid is flowing down. Have you ever seen this? No? It's the same here. When you have gravity, atoms, this is simulation, okay? This is still simulation. But if you have zero gravity, you fill up your bubble. This is a cut in the middle of the bubble. But if you have something like 7 over 1,000 parts of G, it flows to the bottom. Because there's nothing, there's nothing to keep it high. So it was a very beautiful trapping potential with a lot of interesting properties that one could investigate, but we cannot switch off gravity. Can't we? Can we switch off gravity? What would you do if you have to switch off gravity? Send to space. Centrifugal. Okay. You have to rotate a system that is larger than this table. Yeah. It's possible, but it's very difficult. We do a more difficult solution, I think. We send it to space. There is a cold atom laboratory in the space station now to do measurements on very high precision measurements. Okay, so you have seen these interference patterns that I've shown you in the beginning of this lecture. If you measure this with high precision, you can have measures of several quantities. So there was this initiative to send to space. And when they sent to space, okay, this is an experiment that can be done in space and was done in space. So you do switching off gravity, or in the absence of gravity. It's not really switching off. Okay, good. But we can do more. This is a box potential. In 3D, this is a box. You add a wall here, and when I see a wall here, this is a laser beam for me, okay? Repulsive wall on one side, repulsive wall on the other side. In the middle, what you have? A BC in a box. So, and this is quite old. This is from 2005. And people have been studied BC in a box because this is what we solve in our quantum mechanics books. No? But not only that, today there are some devices, they are called digital mirror. You have arrays of mirrors, so you can really draw whatever potential you like. So you can really draw in space this. And they can be time dependent. So you can write things like this. You know what's this used for? This is used to study conduction. This is a reservoir. This is another reservoir. If I make this this thin enough, you're studying conduction. So resistivity or whatever this means. And this is a real picture of atoms on the top and above. And this is a potential that is painted with light. You can paint whatever you like. Again, we are only here. Only here. It can be done more. This is from the Florence group. This is the landscape of Florence, and these are atoms, okay, on the green. These are atoms on a potential that is painted in the shape of the landscape of Florence. This is just for fun, of course. You cannot do really physics with this. But it shows how much we can work with that. And with this, one can do many things. So these are these digital micromirror devices. So they write those potentials in the computer. So this is the binary image. This is the projected light. And when they project this light on the atoms, these are atomic densities filling those trapping potentials. So atoms filling, you know, the face of Einstein. Can you do physics with this? No, of course no. But you can do physics with this. You can do physics with a checkerboard. No? So while this is for fun, you can do many things on this, on these potentials, on this. So we as experimentalists have a huge ability to tune the trapping potential, both static and time-dependent. So one with the right resources and so on, one can really model Hamiltonians, model different quantum systems that you can work in and in a sense, simulate the ground state of these systems. Okay, and this has been, so this is done routinely in labs around the world. So it's quite nice. So that's one of the reasons why Bose-Einstein condensates are very, very tunable. We can study many, many phenomena, but it's not the only, and the story of potentials are not done. Because I was talking about single wells. Okay, here I have multiple, but I was mainly talking about single wells. We can have multiple wells. Double, many, it's what we call a lattice, or 2 and 3D lattices. And these are models for solids. This is how we see a solid, no? These lattice potentials are just light standing waves. Each one of you has done these calculations, how I have a standing wave. It's undergraduate calculation that we do very early. And that's it. You shine it on atoms, and you have a periodic potential. And with this, you have band structure. No? You can have models like the Hubbard model in here. And today, you can even address the sites. Single site. You can, okay, I manipulate site number 24. I manipulate site number 24, and things like this. So we can have, in multi-well systems, simulation of condensed matter, single site addressing, metrology and high precision experiments, and at some point, I've seen that one can do entanglement and basic quantum gates. Exactly how I do it, as I told you, I don't know, but one can, in principle, do this kind of thing, just manipulating the trapping potential. So, yes, question. Just a second. Yes, here.
You said we can easily form any kind of potential, but how long? For how long time can we keep it?
These potentials. So how this works? It's a great question. As I think you notice, I'm not going into technical details here. So, but this is a point. On this devices, these digital micromirror devices, you have like, you can imagine a matrix here, no? 2D matrix. Every element on this matrix is a small mirror that I can change its orientation, okay? So if I shine light, and then the reflected light by these many mirrors is sent to the atoms, this is how I do my potential, or these potentials are done like this. And so this means this is static. The potential itself lives for how long I want them to live. Usually the problem with these systems is the life of the condensate itself. So this is a good question because, you know, I'll give some steps back because I have a lecture tomorrow, so I told you we have to cool these atoms down and avoid that they become a liquid. No, this is what I told you. But I cannot avoid it forever. What I don't show here is that I have eventually 3 body collisions. And this is a loss channel of these systems. Densities on these systems are high enough, this is dilute, but it's high enough that here and there I have a 3-body collision and I lost these atoms. So this restricts how much time I have with my condensate alive. If I am painting these potentials, this means they might be squeezed in some points. So if I squeeze it, density is going up, and of course my time is going down. So and this is of course a problem. So so the condensate lives in these potentials up to 1 second or so. So this is what you have. It's a lot of time for most of the experiments we perform, but it's a problem. No, we cannot live forever. Have these systems living forever. And there is another thing. So these potentials are made of light. Atoms love light, so at some point they scatter photons. This light usually is far detuned from any resonance of the atom. But it's far detuned, but still scattering is possible. From here and there, you scatter a photon. When you scatter a photon, the atom is kicked out of the trap. So these are things that limit the time I have. And to add one more element, every time I make an image of this image that I've shown you, I am destroying my sample and I have to do all the cooling again. So repetition rate on measurements of these things are small. So I cannot have like 1 kilohertz repetition rate, which is not much. No, my experiment had a 1 hertz or 0.1 hertz repetition rate. So it's very small. So you have a limited lifetime, a limited measurement time on these things. So the question was what I mean by repetition rate. Let's say I want to do an experiment with this double well. I have all the atoms in one well. I wait some time and I want to see if some atoms have tunnel to the other side. Okay, it's a tunneling experiment. How do I see it? I take a picture. I wait 100 milliseconds and take a picture. 1/10 of the atoms have moved to the other side. But once I take a picture, I destroy my system. So I have to make everything again, cool everything again, and then I wait 150 milliseconds. In between those, this is my repetition rate, no time between two consecutive measurements. It can be 1 second. It can be 10 seconds. No, it can be 0.1 seconds. Still, it's not large. So it takes time. So I'm selling to you these systems. That's a good point. I'm selling to you these systems this is perfect, we can do everything, we can do many beautiful things, but they are not perfect. There are several restrictions, several experimental challenges to work with this. So still not perfect. Okay. Okay, good. So this is how we manipulate. This is how we manipulate trapping potential. But that's not all. We can also tune interactions. We can also tune this interaction term. But since it's 10:30 and I don't want you to miss the coffee break, I'll say stay tuned. And tomorrow we pick up from this point and go on. Okay? I'll be here for questions if you need. Thank you.